Those would be cotton and sugar. My name is Matt Farrell, and I work here at Cotton Incorporated in the Textile Chemistry Research Department. And I'm very excited to be here this morning and share with you our research around repurposing cotton textile waste and turning it into sugar that we can use for new products. So to get started here, it's important that we ask and understand what is sugar and what are we talking about. We're not talking about grandma pinching you on the cheek and getting a little peck on the forehead. We're actually talking about specific chemical compounds. And so I'm going to show you a couple, and don't worry, there's no test at the end. If there was, I would also have to use Google and cheat, but I just want you to see and see what some of these sugars look like. See what they look like as chemical characterizations. See how similar they look to each other. So these are just very simple monosaccharide sugars. And it's not important that we know what name goes with each one of these, but you've probably heard of some of these like glucose, fructose. There's some other more not as well-known sugars, things like xylose, ribose, and mannose, and galactose. But it's just so interesting in nature how many of these molecules are out there, how similar they are to each other, and how they come from different sources. Once we start putting two of these sugar units together, we start forming more complex sugars, and we call these sugars disaccharides. So there's two of these put together. And a couple of these that we're showing here are probably things that you've heard of before. Unfortunately, if you're lactose intolerant, there's your frenemy there. It's just two sugar units put together, and that's what causes all your problems. If you love malt sugar, maltose here in the middle, and then at the upper right, this is sucrose. So these are disaccharides, again, things that most of us have probably heard of, but never really appreciated what they look like chemically. Once we start putting many of these units together, we start forming polysaccharides or polymeric sugars. So I'm showing you two the natural polymers, sugar polymers that I find are very interesting. So here on the left, if you've ever heard of it, is chitin. So we love eating seafood, right? This is the polymer that's the backbone or in the crustaceans of things like crabs, shrimp, and lobster. And this is the second most abundant polymer that there is naturally occurring here on Earth. To the right, similarly from the sea, is alginic acid. So this is a sugar polymer, and it's essentially seaweed. So it's just really interesting to see in nature how these different sugars are put together, how many units are put together, and the interesting components that they make. So this is a fun slide, and I'm showing you two more, and this is it for the chemistry, and we can be done. Polymers. And so to the left here is starch. If you need a good gravy, there's your go-to for no clumps. And I'm showing you cellulose here on the right. And I'm showing you these two because it's very important to understand that these two sugar polymers are able to give us glucose. And so that's what we're after with the research that we're doing, is obtaining glucose from cellulose. And so traditionally, it's much easier to get glucose from starch. It's a different polymer than cellulose. And so we just have to usually just heat it up. We can add a little enzyme. But when we start talking about cellulose, it's a little bit harder to get that glucose out. It typically requires a little bit more processing and definitely using an enzyme so that we can chop that polymer up and get the glucose out of it. So if we change gears a little bit, why do we care about getting glucose from cotton textile waste? The EPA does a pretty good job of keeping up with all types of waste generation and information, even specifically breaking it down for textile waste. And so the last data that we have, even though the website continues to be updated, is from 2018. And so what you'll see here to the graph and what it speaks to is just, you can see, and this is U.S. information, we continue to produce more and more textile waste. And so for that last data point in 2018, we see that we're generating about 17 million tons of textile waste. And what that equates to is almost 6% of all the waste that's going into the municipal solid waste. So when we're looking at this graph, we see that it's interesting that we are increasing the amounts that we're recycling and being able to get energy out of by combustion. But when you look at the rates, we also see that we're continuing to throw away more and more into the landfill. So essentially that rate for recycling stays the same. So why do we care about this? What this shows us is there's a tremendous opportunity to utilize textile waste if we can find something to do for it. And so, of course, what does that mean if we want to use textile waste as a feedstock? One of the things that comes up that you see as an argument against trying to utilize feedstocks to make things from a bio perspective is if you're utilizing a food source. Obviously, the old clothes you've thrown away and don't want anymore aren't a food source for us anyway. And so that's a great selling point. This presents itself as a potentially free feedstock, but in reality, there may be some type of grading, sorting, things that you need to do to get that ready to be utilized. And of course, you're going to ship that back and forth, say, to a plant. So in the past, the cost of, say, natural gas and oil, excuse me, has been, so cheap that there really hasn't been a big push to look at things like bioethanol or other bio-based chemicals. They've been around, but it's just been so much cheaper to make them from those petroleum or gas derivatives. If you're speaking to specific other feedstocks that have to be grown, take corn, for example, or those derivatives, you're going to have to grow it. You're going to have to buy it to be able to get that sugar out of it. And then once you start talking about a cellulosic bio-based feedstock, whether it's switchgrass, whatever it may be, those are also more expensive. And so we sort of see this trend when we review what's been going on. But the takeaway here is textile waste is out there. If we can find something to do with it, great. If we can find something to do with cotton, that's even better. So if we start talking about specifically cotton-based feedstock, so depending on who you ask, what time of the day it is, if the stars are aligned, you're going to get a little bit varying information. But generally, the thing to understand here is that the cellulose content that's in cotton fiber is going to be somewhere from the high 80s to the mid 90s. And then the rest is just a small percentages of things like protein and pectins and minerals, waxes, and other organics. What's important, and if we take a step back and think about when a fabric is prepared and it finally gets to somebody like me as a textile chemist, we've processed that fabric and we would refer to that as prepared for dye. So whether that's been bleached or scoured, just to hopefully this resonates that fabric is essentially pure cellulose. So that means that fabric in that state could theoretically be turned into 100% glucose. It's just a crazy, interesting, and as a scientist, it's very, very interesting and is exciting. The other side of that coin is, though, as we can all appreciate looking around our closets, those final textile products, whether it's sheets, towels, clothing, whatever it may be, they're all kinds of different colors. So again, us as the textile chemists, we put on other kinds of chemistry and dyes and finishes and, of course, sewing threads. So we've diluted that cellulose a little bit. But the overall thing to understand and appreciate here is there's just a huge potential to take cotton textile waste and turn that into glucose. So, of course, everything sounds great. And, of course, there's always a challenge. And so what is that challenge with cotton textile waste? Well, the challenge is the crystallinity of cotton cellulose. And so to my knowledge, cotton cellulose is the most crystalline cellulose that you can find. And if you're not familiar with crystallinity, think of the story of the three little pigs. When we talk about crystallinity, we're talking about how well ordered and structured a polymer system is. So that little pig that made his house out of straw, it's way easy to get in there and get that bacon. If you compare it to the pig that made his house out of the bricks, you're really going to have to work hard if you want to get in there and get that ham. And so I know that's a cheesy analogy, but just to give it some type of context. So we have to do something that allows us to disrupt that crystallinity within the cellulose found in cotton. And when we look back over the years, we see that this isn't necessarily a new concept, but from my perspective, when I look at this, I see that the research that's been carried out really relies on, and you'll see this word from me, exotic methods. And what I mean by that is you might have a solvent with 10 syllables long that you can't pronounce. It might be extreme conditions in terms of temperature, pressure, or just very high levels of solvent or chemistry, things that aren't very appealing to do that would be hard to scale up. And so when we started this research, we laid out a couple of objectives. I like simple. I want things to be simple. So we wanted a simple process. And we wanted to have a process that didn't utilize these exotic methods, nothing that's going to be hard to handle, hard to do, unrealistic. And for some of the reasons that we were talking about earlier, we had a realistic expectation starting out that if we're using cotton textile waste as a feedstock, we know it's going to be hard to get that sugar out. Then we might not be as good as, say, a corn base or starch base sugar in terms of yields, but that's okay because we're taking a waste product. Whatever we develop in terms of a process, we want to be able to put this on actual end-of-life textiles to see how this process works. And then, of course, the sugar that we're making, we want to be able to evaluate that in some methods so that we ensure that the sugar that we're making or the glucose can be utilized downstream in another process. An easy example would be fermentation to make ethanol. So what we've developed so far are two approaches. So what you'll see here to the left of your screen is an approach that we've developed in-house here at Cotton Incorporated. And we've patented this approach. And the whole basis of this approach is a one-pot novel process so that we're able to chemically pre-treat in one pot, whether it's a reactor, whether it's a beaker, whatever scale we're talking about. And we're actually able to pre-treat it and then add the enzymes and make a happy environment for the enzyme to hydrolyze the cellulose and produce glucose. So it's very simple, it's straightforward. Even I can do it, which is amazing. But as we move to the right here, I think one of the strengths that the researchers here at Cotton Incorporated have is we're able to interface with researchers, whether they're from government, academia, industry, and really develop close collaborations to leverage research. So what you see here is NC State University has been a great research partner for us. So we shared with them what we have developed to date, and we went on to develop another process with them that instead of relying on a chemical pretreatment, relies on a mechanical refinement to open up that cellulose to allow the enzyme. And so the result of this work is we're able to get very high conversions, nearly complete conversion of cellulose in some cases. What you'll see at the bottom of the figure on the right here is this research also developed a very novel decolorization technique. So what that means is when you're looking in your closet and you see all the different colors that the dye chemists and textile chemists have put on to make those different garments, some of those are a problem for us in this process, but now we're effectively able to remove those dyes, and you'll see there on the right the representative colorless starting from black, so that if there is an issue with the dyes, it's not going to impede the hydrolysis. So to give you an idea of what this cotton to sugar process works like for our in-house method, you see a cotton dress shirt here on the left. That shirt is ground into a powder. And it's added here into a beaker where we add in a dilute amount of acid and we heat that up to form a slurry. So within that same beaker, we cool it back down. We add some other chemistry so that we're effectively making a buffer. In other words, we're giving that enzyme the exact pH that it likes to be able to go in and hydrolyze those cellulose polymers to produce glucose. So we let this sit for a couple of days at a slightly elevated temperature. We come back, we filter that. And so what you can see here is at the top of that filter paper, we have some recalcitrant residue, things that didn't break down, things that didn't hydrolyze, maybe sewing thread. There's definitely some dye in there. And we filter that through vacuum filtration. And the resultant hydrolysate here on the right is nothing but a sugar solution. So it's just really amazing to see what you can do with a cotton-based textile. Another thing that's really important about these processes is previously we mentioned sorting. Well, this process and the process at NC State, they don't really care about the inclusion of synthetics or polyester. So this makes it very appealing that you don't have to sort garments. Of course, it wouldn't make sense if it was a low cotton percentage. But you can see here a demonstration of a 60-40 cotton knit shirt. At the end of the process, the polyester is just spit out and filtered out at the end, did not interfere at all with the process. Similarly, here to the right, we have a cotton poly dress shirt. Again, that polyester is just removed and filtered out at the end of the process, and we obtained the sugar that was in the cotton-based portion of that shirt. Taking a minute to look at the process from we developed with NC State, what you'll see here on the left figure is a pretty gnarly looking grinding wheel. So this is a lab scale PFI refiner. And so what happens, the principle of this machine is we create a very fine gap between the wall and this wheel. And as this revolves and the cotton is between that gap, we basically fibrillate the cotton or the cellulose and open it up. So the micrographs on the right side of your screen here, you can see at the top, this is what a fiber bundle looks like with no refinement. Everything's nice, it's intact. But as you can see in the bottom of the figure, after 10,000 revolutions, we've pretty much opened that fiber up, we've fibrillated it. And that's really important because as we talked about the crystallinity, this allows that enzyme much easier access to get in to that cellulose and turn it into glucose. And so that's why the efficiency can be so high with an approach like this. So in early 2023, we were able to take that approach with NC State. They have a pilot line set up within their college of natural resources. And so what you'll see here to the left is a pilot scale PFI refiner. And then that middle picture here is just a vat where we did the hydrolysis, carried that out over several days. So this was a successful trial for us. Really excited to get that accomplished. So for me as a researcher, I try to compartmentalize. We are trying to think ahead of what we can possibly do with these sugars, but it doesn't make too much sense to concentrate on that if we can't actually create those sugars first. And so we did something fun with this, and we took about 5 gallons of the sugar that we obtained for this. And I think we've all heard of the cotton gin, but have you ever heard of cotton gin? So this was a playful thing that we did, absolutely pun intended. We concentrated this glucose and sent it to our colleagues down at the USDA to see if we could actually develop a cotton gin made from cotton textile waste. And so in the end, we've unfortunately been unsuccessful so far, and I refuse to believe that it was my old underwear and socks that were the problem. But, you know, these are biological processes. They can get contaminated, but this was our first effort to show and, you know, demonstrate clearly that we could make something new from cotton textile waste. And how fun would that be to hand out to everybody? But in all seriousness, when we developed the glucose, there's really two paths you can take. One would be to utilize the glucose as is and do some type of chemical reactions to it. The others are bio-based or biological processes rather. And so this year we've been doing some really exciting research with Thomas Jefferson University. So we're creating the glucose here in our labs and supplying it to them. In turn, they take the glucose solutions that we're producing and they're feeding it to a specialized bacteria. This sounds funny, but when you stress the bacteria, it actually excretes this P3HB biopolymer. And so here you can see the setup for this reactor. You can see a sample of that polymer on the right. And why this is so exciting, why this is so important, is this polymer in its final form takes on properties that are similar to polypropylene. So imagine just all the everyday products that you might have around the house that are made from polypropylene. What if one day we could actually make those from this polymer that's actually made from cotton textile waste? It's just really exciting research, and we're going to keep continuing that research this year, and excited to see where that goes. So another example, and don't worry about all that going on in the middle, is we're going to be working with UMass at Lowell this year. And so they have a specialty yeast so that we will be supplying them, again, with glucose that we've made. But if you focus onto the far right there and just see those different pictures, this yeast is able to make different oleochemicals. And so what that means is, imagine being able to make fuel additives or lubricants or even omega-3 fatty acids, all types of just fatty chemicals, all made possible by this yeast utilizing glucose that's produced from cotton textile waste. Again, we're starting that research this year. Just really excited to see where this is going. So I think it's important to highlight that while we're on this journey and the work that we're doing, we try to put out this information, whether it's journal articles where we can reach other academic researchers, hopefully inspire them. We've seen how well those collaborations work. Somebody might have a newer idea, a better idea of how to do this. Whether it's blog posts, whether it's press releases, whether we're getting press from the press that's interested in what we're doing. We're really just trying to get this message out as we're on this journey. And I think it's really important to show those that are in this stakeholders what is important with cotton and how you can do so many new and interesting things. And so it's really important that we communicate that. So as our current state here, the chemical pretreatment process that I showed you, we've patented that here in the US and several other countries. We're trying to do that same approach excuse me, with the mechanical refinement. And it's important to understand why we do that is we want cotton stakeholders to be able to utilize this type of application without being prohibited by some other entity. So we see the importance of cotton textile waste. We see what it can do. We see the potential new products. And so we want to ensure that our stakeholders are able to do this type of very exciting technology. We've signed an agreement with a chemical company that we've been collaborating very closely with, I'd say, for the last year and a half. They're really, really good group of people. You can see yours truly here in the plant there at that top picture, staring at a reactor, wondering why I always choose the hottest day of the year to go do something like that. But, you know, it's a great experience for me. It's a great experience for cotton. You can see cutting waste there. We're collaborating with a major brand that's supplying us cotton cutting waste. So this would be waste before it gets to the consumer. And we're hoping to utilize that waste in the pilot trials at that chemical plant. And you'll also see here in these bottom pictures, we sourced our first bale of post-consumer textiles. And I'll have to tell you, you haven't lived until you've seen the sights and smelled the smells within a bale of used donated clothing. And I'll call your attention there to Mary Ankeny's hands. We sort of had an impromptu little contest when we were sorting through this to see who could make it the longest without putting gloves on. I don't know if I should be proud of the fact that I made it the longest, but I did it. And we've just met some really good people, really good groups of people that are really interested and are supporting us in this research. And it's been great so far. So I want to leave you with one or two final little takeaways. If you didn't know it already, cotton is sweet. And so I think we've all pretty much thought about that from a figurative perspective. But hopefully now you understand that quite literally, cotton is sweet. You see the work that we're doing here to turn cotton textile waste into sugar. And so very exciting. We're very excited to see where it goes as this continues to develop. And I'll leave you with one final, if everything will work correctly, animation that was put together, I think, for Earth Day in 2023. It's just a very short and sweet, no pun intended, video that does a really good job of summing up the research that we're doing, what we're trying to do. I'm Matt Farrell, and my focus is on sustainable initiatives for cotton. Traditionally, when you've reached the endpoint life of a garment, you can either repurpose, recycle, or dispose of it. One of the newest and more interesting things that we are researching is taking textile cotton waste and turning it into glucose, or more commonly known as sugar. Glucose as a starting material can be made into bio-based chemicals that are used in everyday products and consumables such as detergents, cosmetics, and other polymers. This exciting research presents a new opportunity to create new things from cotton textile waste. Awesome. Well, that's it for me this morning. I hope we were able to enlighten you with some of the work that we're doing. Hopefully you found that exciting as we do.